Right, so in chapter 3, we're going to talk about derivatives, right? Derivatives are what makes up half of calculus, basically, okay? So like one half of calculus is about derivatives and exploring them. So let's start with the definition of a derivative, okay? So the derivative of a function f, and we say with respect to a variable x, is labeled as f prime. Okay, so the derivative is labeled as f prime. And it's found using this formula. So let me ask you this. Have you seen this before? Have you seen the right-hand side of this equation? Where have you seen it before? What is that? What? Okay, so what is it of the tangent line? It's the slope. Okay, so you know this as the slope of the tangent line. It's been your buddy since last year, right? Or, you know, you've grown to love it now, right? So it's the slope of the tangent line at a point, right? It's also, right, the instantaneous rate of change. And now we have a new term for it. It's the derivative. Okay? All right. So nothing new here, just a different name for it now. And in fact, I always tell my AP students or my calculus students to repeat this like 10 times every day. This is like your, you know, like your math prayers, right? Like slope is derivative, derivative is slope. Slope is derivative, derivative is slope. Because guess what slope is? Derivative, right? And guess what derivative is? It's slope of the tangent line. Okay, so some more terminology. If f prime of x exists, we say that f has a derivative, or another word for it is we say f is differentiable, so it's possible to find its derivative. Now, if a function is differentiable at every point of its domain, it is called a differentiable function. Very clever title there, okay? Now, some more notation. So we know that y can be called f of x, right? So if we have y equals f of x, some notations for the derivative are f prime of x, right? And we read that as f prime of x. We can also call the same thing y prime, okay? We could call it dy dx. That's how that's read, okay? Not dy, it's dy dx. Okay, that's the cool lingo, okay? Dy dx, it means the derivative of y with respect to the derivative of x, or with respect to x. Since y and f are the same, it's also called df dx, okay? And so if I write that dy dx, where is the function here? That's the y, right? So if I isolate that function and I write it alone, then it looks like this, right? And as it turns out, so y is the function. As it turns out, this d dx is what we call in math an operator. And you've worked with operators before. All of these are operators, okay? Plus, minus. And so your brain, it's just like coding. Your brain is programmed so that if it sees this sequence, right, number, operator, number, your brain, it's programmed just like a computer language would have programmed it, that when you see that sequence, you do a specific operation to it, right? Like to an alien, like to somebody from another planet, that would be meaningless, but it means something to you. So same thing, the ddx is an operator, and whenever you see it next to a function, your brain is now programmed to say, take the derivative of that function. Okay? All right. So, okay. We're going to differentiate or find the derivative of x cubed. F of x equals x cubed, right? Okay. So let's start. We're given f of x, right? So now we're going to find df dx. You could also write f prime of x. It's the same. And we're going to do limit as h approaches 0, x plus h cubed minus x cubed over h. If you recall, in the past, when you had to do this, right, the f of x plus h minus f of x over h, when you had to do this, students, you would always ask me, so do I now call it m? And I was always like, yeah, whatever. I always avoid giving a direct answer. I never give a direct answer because I know that eventually we're going to find what to call it, and we're going to call it f prime of x, right? Okay, so this, let's simplify it. You may or may not remember the formula for a binomial cubed. I'll tell you, it's x cubed minus 3x squared h. I'm sorry, they're all pluses. Plus 3xh squared plus h cubed minus x cubed all over h. Okay? And then getting rid of these. What else are we going to get rid of? We're going to get rid of some h's, 1, 1, 1, and this one. So what I have is limit h approaches 0, 3x squared plus 3xh plus h squared. Right, so when I plug in h as 0, f prime of x is 3x squared. And this is nothing different than what you've been doing. The only difference is we now know what to call it. We're not calling it m anymore.
So it's not m tangent anymore?
No, now it's the derivative. Okay.
And before, technically, in our last test, we were finding the derivative too.
Yes, yep, you just didn't know. But that's what you were doing, yeah. Right, but see, that's the thing is, what is a derivative? It's the slope of the tangent line. You have to know where it comes from. Okay, and because, one definition for something is never enough, we also have an alternate definition of a derivative at a point. Okay, so let's see where this comes from. Where did the whole f of x plus h business come from? Remember how we had said if you have x here and you go a distance h, then you have another value x plus h. You remember that? And so this was f of x, and this was f of x plus h. And that's where the whole f of x plus h minus f of x over h came from. You remember? Okay, but this just seems like it's too crowded, right? We can simplify that. We don't have to call this x. We don't have to call that x plus h. I can call this banana and happy face as far as, right? And this will be f of banana and f of happy face. Like, what difference does it make? Similarly, I can call the first point a and the second point x. And so now this becomes f of a and f of x. So now what will the slope of the tangent line be? Well, the slope of this black secant line will be f of x minus f of a over x minus a, right? y2 minus y1 over x2 minus x1. Now, what we did in order to make it a tangent line is we would bring that point closer and closer to the first point, right? So if my values are a and x, as I bring that point closer and closer here, what happens? X takes on what value? A. So there is no more h. So the limit becomes as x approaches a. Okay? And this is a much quicker way of finding it. So this way we eliminate h. Okay, so with this new formula, let's find f prime of 2. Okay? All right, so what are we doing here? We're going to find f prime of 2. What does that mean, f prime of 2? We want to find the slope at a equals 2. Okay? Okay, so f prime of 2 is the limit as x approaches a. Whoa. So what's the formula called for? F of x, which is root x minus 1, minus f of a, right? And what's f of a? It's root 2 minus 1, which is root 1, so 1. So minus 1 over x minus a, x minus 2. Okay? Now we have a problem here. What's the problem? Huh? Right, so like if I plug in, I'm sorry, this is x equals 2. So now if I plug in 2, I get 1 minus 1, 0 over 0. That's not cool, so I need to get rid of it. And I need to get rid of it like pre-calc honor style, like we did last year. Remember the roots that we were doing last year? What we used to do, remember, was multiply by the conjugate, so it's the root plus 1. And remember to do it on the denominator as well. Some people are still forgetting. So limit as x approaches 2. Multiply so it's the first one squared, so x minus 1, minus the second number squared, 1, over x minus 2, x minus 1 plus 1. I know you want to multiply that in, but don't, right? Because it's going to cancel. So this is limit as x approaches 2, x minus 2 over x minus 2, x minus 1 plus 1. This goes away, this goes away. Look at that. This is the limit as x approaches 2, 1 over root x minus 1 plus 1. And then you can plug it in. You can plug in the 2. So you get 1 over root 1 plus 1, which is 1/2.
The second part, right? X minus 1, so you got x minus 2 times plus x minus 2.
So what we've found is that f prime of 2 is 1/2. What does that mean? The derivative at x equals 2 is 1/2. What does that mean? The slope of the tangent line at x equals 2 is 1/2. Okay, so next, we want d dx of 3x squared when a equals -1. Now this is a different notation, and I'm going to teach you guys another way to write this stuff. Calculus has like its own world of like writing things, right? Its own notation, its own little code. Okay, so what we want to find is the derivative of 3x squared evaluated at x equals -1, okay? So let's look at what this is asking us. The derivative of 3x squared where a is equal to -1. So yes, that's called a because we're looking at a as a constant. Here, the notation is the derivative is x, the variable is x, right? So when you're evaluating it, it also has to show up as the variable x equal to -1. So whatever you put here, it has to show up in your derivative, in your function. So now, same situation, right? A is -1, so it's going to be the limit as x approaches a, which is -1, of f of x, 3x squared, minus f of a, is 3 times negative 1 squared, 3, over 1. No, over x plus 1.
Is it minus? Oh wait, square and minus.
Yeah.
Wait, why is it plus 1 and not negative 1?
Because it's minus 1. It's x minus a.
And then also, why did you write x equals negative 1 before the...
Here?
Yeah.
Because we're saying let's evaluate the derivative at x equals negative 1, and this is the notation. Evaluate the derivative at x equals negative 1. So that's notation. So what you're saying is the derivative of 3x squared evaluated at x equals negative 1 is this.
Okay, but it says a equals negative 1.
Right, so that's what I was saying before, is it says a there as a constant a, but in the notation, it has to be the same variable as the constant, as the function. Okay. So factor out the 3, we get x squared minus 1. Limit x approaches to negative 1. 3 x minus 1, x plus 1, over x plus 1. Okay? So cancel that. And now I can plug in negative 1, so I get 3 times negative 2 is negative 6.
Would the units still be the same as like
Yes. Yep. Because it's the change in x, in y versus the change in x, so it would be identical. Yep. Yes.
So how would you write that? Would you write f prime of negative 1 equals 6?
Well, okay, so that's the thing, is you can't use f prime notation now, because to use f prime, you need the name of the function. But here you're not given the name of the function. It could be called y, or it could be called z, or f of x, or g of x. So your only option is to write it this way.
Okay, so ddx is raised with 1.
Right. So when you have ddx, you can put the name of the function, f or y, or you can put the actual function.
Okay.
But when you have f prime, you can only put the name of the function, not the actual function.
And then instead of x, would you put negative 1 on the ddx, or no?
Here?
Yeah, because then you have to put that a equals negative 1 somewhere.
I did. See here, it's right here.
Oh, that's
Yeah.
Okay.
Yeah.
Quick question, Ms. Malikian. So this one,
A very large portion of calculus is also finding and looking at the relationships between a graph and its derivative. So we just said that a derivative at a point is basically the slope of the function. So if we do that, then we can take a look at a graph of f, and we can estimate the slope at various points along the graph. So for some functions, you can get the slope exactly, and then some other functions, you're going to estimate the slope, but that's fine. So let's do that here. All right, so here we want to graph the derivative of the function f, whose graph is shown. The derivative is the slope, right? We're given f of x. We want to graph f prime of x. All right, so we want to look at the slopes. Well, take a look here. What I have is a function made up of linear segments, and it's very easy to find the slope of linear segments, right? So, but you can see here I have 4 different segments. So naturally, I want to partition into different segments here. Okay? So in the first segment, the slope, like algebra 1 style, rise over run, is 3. Here, 0. Here, minus 1 and 1. 2, yeah. So now, look at what this says. In the interval from 0 to 1, the slope of this is 3, a constant 3. So in our interval from 0 to 1, the slope of that function is a constant 3. Okay? So just leave that like that for a minute. Okay, and I'm going to come back to that in 1 second. Here, from 1 to 3, the slope is 0. From 1 to 3, the slope is 0. Okay, let's look at the boundary. Here, at that corner, immediately to the left, the slope is one thing. Immediately to the right, the slope is another thing. There is a little bit of like a discrepancy, a discontinuity, if you like, in the derivative there, in the slope. So we put a closed circle here, but here in the middle of the graphs, we have to put open circles, because at that point there is a little bit of a what's the word? Right, but like the word I'm looking for, like there's a little bit of like a controversy as to what the slope is there, right? So we want to leave that open, and we're gonna come back to that this whole chapter. Exactly.
Not like infinitely small.
No. So what? It's 3 and then 0. There isn't a gradual change. It just changes like that. So in that spot, Jonah hit it. Like it's like it doesn't exist there because it's changing. Don't dwell too much on this right now. This is what this whole chapter is about.
Okay.
Next, the slope is -2 from here to here, and then the slope is 1 from here to here. Oh, so remember to put closed circles at the ends and then open circles everywhere in the middle. Okay. So this is a function where the segments are linear, so they have constant slope. This is where wherever you are on the graph, you have a different slope, right? So look at this. As you move along here, the slope is changing at every point. So this is going to be a little bit of a different situation. So here's what we're going to do. When I'm here, I'm going to call this point A. I'm going to sort of, what do you call it? Like exaggerate this a little bit, right? Just that slope there, right? The tangent, I'm going to exaggerate it a little bit. So do you see how the tangent there, it looks like it's about a slope of 4, right? So I'm going to say, so if this is point A, I'm going to say A prime is roughly 4.
That's what it's saying, because like you're going off on a tangent, you're starting off on a point graph, it's going different line.
It's exactly what it is. Like you just went off on a tangent. That's exactly what it is, right? That's where it's exactly where it comes from. Here, do you see how the slope is 0? Let's call that point B, and we'll say B prime is 0, right? We're estimating. And then, let's pick another point, C. I'm going to pick one here at x equals 2.